Hi, welcome to Equilibrium 2. This is Ms. Dahlberg. Let's go ahead and get started. We are talking about Gibbs free energy and equilibrium, or in other words, we're comparing delta G to K and seeing how those guys are related today. So let's go ahead and start. What is delta G? So delta G is Gibbs free energy, and it is how much work can be done by the system. So if you have a negative delta G, what does that mean? So we talked about thermodynamically favored, and what that means. If delta G is negative, it's thermodynamically favored. What does that mean? It means that if you have a reaction and it's going to proceed in the direction of the products, then a delta G of less than 0 is what you would have for that reaction, or that reaction is thermodynamically favored. And so if it is positive, then it will not proceed in that direction. The reverse reaction will be favored. And so today we're going to talk about if a system's at equilibrium. We know that the concentration stopped changing, and so delta G is 0 because that system is no longer available to do work. And so the forward and reverse reactions continue to happen, but the rate is the same now. And so there are no changes in concentration anymore. And so how does that affect the system? And so looking at a graph like this, if we look at A and B, A is our reactant, B is our product, and we have the G value for A and we have the G value for B. And if we look at that, G has a higher value for A than for B. And so if we calculated the products minus the reactants, we find that in this case we get a negative delta G. In other words, going from the reactants to the products, there is a release of energy. And so if we look at this, the forward reaction is favored. It's negative. The reverse reaction going up the hill, and we'll kind of jump down here to the red one, going up the hill toward G, is not favored. This point is equilibrium, and we would expect the equilibrium to be here. If you have pure A and you have pure B, in the middle, say this is the middle, this is the halfway point, you would have half and half. Since delta G is negative, we would expect the equilibrium to lie somewhere closer to our products, because a negative delta G means it's product favored. Now, if we had started with all of the products, this reaction going this way toward equilibrium will be favored. But when it reaches equilibrium, it's going to, again, have more of our products than our reactants. Now, to go all the way back to our reactants will not happen because that's thermodynamically not favored. All right, we have a positive delta G to go up this energy hill. And so to get there, we would have to add energy in for that to happen. If we look at that, at equilibrium, if delta G is negative, it favors our products. And so if it favors our products and our K is products over reactants, we have a whole lot more products and reactants. And so we have a really big number, much greater than 1 for K. And so now this reaction, depending on where you start with reactants or products, it doesn't matter. It's going to proceed to equilibrium in either direction. And it's going to proceed that way. And if delta G is negative delta G, or our other word is thermodynamically favored, it's considered to be exergonic, meaning you can get energy or do work with that reaction. Now, if we look at this one, let's look at the reaction of C becoming D. Now, C is our reactant, and here we have pure C, here we have pure D. And if you look at the delta G for just C and the delta G for D, we have an uphill journey. So we start with just C. The reaction will proceed toward the products. We have a negative delta G until equilibrium. Now at equilibrium, because the energy of C is less than that of D, it's going to reach equilibrium on the side closer to the reactants. And so we have a combination right here of reactants and products, but there's more C than D because this is a product favored reaction. How do we know it's a product favored reaction? When we take the delta G's and we subtract our products minus our reactants, we get a positive number. And a positive delta G tells us we have mostly reactants in the equilibrium mixture. And so this kind of process is an endergonic process. That is whenever you have a delta G that's positive. And this favors reactants at equilibrium. So you're going to have a really, really small value for K because, again, K is products over reactants. And if we have a lot more reactants than products, this is going to be a really small number. This is going to be a really big number. And so we're going to see a really tiny number for K. So it's going to proceed to equilibrium in either direction. But at equilibrium, there's just going to be mostly reactants, hardly any products. So now, could we get, we don't want reactants, we want products. Could we get products? So if we use Le Chatelier's principle and we take those products and remove them, it will shift to produce more products. So we can still get products from that kind of reaction. We just have to do a little something to get more products because it is a reactant favored reaction. And so at equilibrium, now this is our first graph again. At equilibrium on either graph, at this point, delta G is 0. The change in G is 0 at equilibrium. And so at this point, the reaction is no longer changing concentrations. It's no longer able to do work. And so you have equilibrium. And anytime you have equilibrium, delta G is 0. Okay. And so when we talk about G naught, this little looks like a degree sign. Just indicates that it's at standard state. And this just kind of goes through what that means is you have pure substances. If it's a gas, it's at 1 atmosphere. If it's a solution, it's 1 molar. The temperature is 298 Kelvin, which is about 25 degrees Celsius or room temperature. And so now equilibrium exists at other temperatures. So if we don't have standard state, the temperature will be indicated by a number right there. And so delta G naught is the work that can be done by a system as it moves from 100% reactants to 100% products in their standard states. So the delta G at a temperature is when you are finding the work that can be done as it moves from reactants to products at those non-standard temperatures. And so that's what that little degree symbol stands for. And whenever you see a temperature down there, that's why that's written there. And so let's relate delta G to K. Now this is what I call the negative Ratlink equation that links delta G to K and how we can calculate the difference between the two. And so if we know that delta G is negative Ratlink, the R here, now this is a different R than we've been using. Before we've been using the gas law R, this is the energy constant. And so this is the first time, and this is the only time we use this number. Now, how will you know when to use this number? Delta G needs to be in energy units, which are joules, and this is the only gas constant that has joules in it. So we want the energy constant. All the other ones have liter, atmosphere, stuff like that. And we want energy in joules, not atmospheres. Now, T is the temperature in Kelvin, the natural log of the K. Now, if we look at that, if we wanted to get this equation in terms of K, it's already done for you. I'm just going to kind of show you how they got that number. If you want this in terms of K, step one is to get K by itself. And to do that, we would want to divide both sides by negative RT. And on this side, the negatives and the RT cancel, leaving us with a negative delta G over RT equals the natural log of K. Now, we don't want it in terms of natural log of K, we want it in terms of just K. And if we get rid of this natural log, in order to do that, we need to do the opposite. The opposite of taking the natural log is e to the power of. And so if we raise both sides of this equation, and those become the exponent to e, then this side becomes K, and this side becomes e to the negative delta G over RT, and that is how we get this equation here. And so these two equations, this one is on your equation sheet, and you can use that for information. Now, most of the time, you are going to kind of estimate K from G. In other words, if delta G is positive, your K is, I don't know, if you have a positive delta G, that means it's mostly what? Mostly reactants. Yes, it's reactants favored, and you produce hardly any products. So if you look at K, if K is always products over reactants, and we just said you have mostly reactants, this denominator here is a really big number. So you have a really small K. K is going to be much less than 1. And so how could you calculate that? If you're looking at this equation, and if you're looking at this RT value, if you have a temperature of 298, and so in here we plug in 298 or 300, and R is 8.31, but if we plug in 8, that's a good estimate. This term here becomes 2400. And so if we look at delta G and kind of estimate, if delta G is much greater than 2400 joules per mole, then K is going to be really, really small, meaning this is going to be a really positive number. This is, when we solve for K, this is going to give you a really small number. If it's somewhere between 2400 and negative 2400, then, well, you have, K that's kind of in the middle, almost even amounts of products of reactants. It's hard to say. You'd have to kind of calculate that to know. But if you have delta G that's much, much less than negative 2400, I mean, you have a really negative number. Really, the magnitude is big, but it's, a very, very big negative number. Then when you solve this, you put in that big negative number here, it's going to become a positive. You're going to have a really, really big K, meaning you have a lot of products and just a little bit of reactants. So a couple of ways you should know if you have a really negative number here for delta G to expect a really big number for K, and vice versa. You should have a really, really small number for K when you have a positive number for delta G. And so moving on, could you estimate it? Now, I don't think you're going to have this ambiguity with these questions. So I'm going to eliminate choice B and choice E. And let's look at these three for this situation. So you have a reaction and you have delta H is negative 20 kilojoules and delta S is negative 100 joules per Kelvin. Which of the following statements provides the best description of the system at equilibrium? So does it contain mostly products or mostly reactants, or is it somewhere close to the middle? So how would you do this? So maybe the first thing you would look at is taking these two numbers. What would you do with those guys? Absolutely. You would want to find delta G. And so if you look at that, if you calculate delta G, now let's pretend this is a multiple choice question. We can't use a calculator. And we already recognize that, hey, I recognize these two guys are never the same unit. So I'm going to convert them to the same, and it doesn't matter which. In this case, we have converted to joules. So this is 20,000 joules instead of 20 kilojoules. And right here, we plug in our 100 in our going home to supper, and we're going to estimate, since we can't use a calculator, instead of 298, that becomes, that's close enough to 300. And so we'll plug in 300. And so after we do that, that's a little bit easier math. We have negative 20,000 minus a negative 30,000. And so we get a positive 10,000 joules. And so if we have a positive 10,000 joules, that's a pretty positive delta G. Now we can come over here and we can look at that. If we plug that in, if it were one where we could use our calculator, we could plug in our delta G right here into this equation and take E to the whole thing. You know, we could open up our parentheses, put in negative, whatever the answer to this was, divided by R and T, and we would get this really, really small number when we do this. It's like 0.01 something. But in a multiple choice question, we don't even have to do all of this work. We can estimate using delta G. Now, if you go back looking at this, does it contain mostly products, mostly reactants, or is it somewhere close to the middle? Well, if delta G is positive, our K is going to be really, really small. And so we're going to have virtually all reactants, or mostly reactants, in that system at equilibrium. Okay. So looking at this, here is another problem. Now, it says for the above reaction, we know delta H and we know delta S. And we want to know what's the value of Kp at 298. Okay. And so step one would be to use these two guys and find delta G. And so finding delta G, we would do the going home to supper equation. And so if we had going home to supper, to find delta G, we took our delta H value and plugged it in. We took our delta S value and plugged it in. Our temperature of 298. Now, again, the fatal flaw for one of these, make sure the units match. So I'm going to give you a minute. Go ahead and do this. And so if we plug in our numbers, we have negative 198,000 joules and minus, I'm going to open parentheses here, 298 times negative 188, and we get negative 142, or kilojoules, or negative 142,000 joules, which tells us what for K? How could we get K from this? So this tells us, first of all, that we have a lot of products. A negative delta G means it's a very exergonic reaction. It's thermodynamically favored. And we produce mostly products. And so our K is going to be a really big number. Now, if we look at that, to find K, we would use that negative Ratlink equation. And so if we know delta G, we can put e to the, and we can put in our delta G. And so we have negative delta G, and delta G is negative 142 joules divided by the 8.314, that's the R value that you use, divided by our 298. So all of this is in the denominator, and this is in the numerator. And so when we multiply and divide these two numbers, and again, pay attention to these negative signs, we're going to end up with a positive number for this whole thing. We get a K of 7.78 times 10 to the 24. Make sure you do this in your calculator and that you are able to use your calculator to come up with this answer. So you can obviously use your calculator to do this again. Now, I said this was going to be a very big number. It is a giant number, which means that we have an equilibrium that's practically all products, which is exactly what we said that we expected. Okay. So now here is a problem. We're going to kind of skip part of this problem, but if you have this reaction, nitrogen and hydrogen form an ammonia, and you are given the case C, it tells you to find delta G. So step one, you're given case C. Now that equation, I kind of went over this kind of quickly, but whenever you do that negative Ratlink equation, you're using Kp. Now, I told you you're not going to have to convert from Kp to Kc unless the number of moles don't change. And so in step one, instead of finding Kp, we're just going to write down the answer to use it in the next step. And so if we look at this equation, I told you we're not going to be doing this unless delta N is 0, and this all becomes 1, and Kp equals Kc. But in this problem, it's not, so just go ahead and write down Kp equals 36.5, and then we'll use that in the next step. So if we are looking at this, we're trying to find delta G. So if we're trying to find delta G, and we know K, we know K is 36.5. We can use our negative Ratlink equation. So we know the R value, that's a given. We know the temperature. The temperature was given as 400 Kelvin, and the natural log of K is 36.5. And so when we calculate delta G, we get negative 1.2 times 10 to the 4th, or negative 12,000 joules per mole, or negative 12 kilojoules per mole. And actually, 12.0, I don't know that we could show sig figs with this number. written like this. So we would have to write it in scientific notation or kilojoule notation. Okay, last problem. Let's look at this one. This is number 8 from the problems in your homework. We're given a reaction. So we have PCl3 and oxygen going to POCl3. We're given the delta H and the delta S. Now, anytime you're given the delta H and the delta S, your first thought is, I'm given the two things that I can calculate delta G. So probably I'm going to be asked to calculate delta G, and in fact, we are. Problem A says calculate delta G. And so when we do that, now we can look at this and maybe try to predict. If you have a negative delta H and a negative delta S, is that thermodynamically favored? Well, I know if this is negative and delta S is positive, it's always thermodynamically favored. I know if this is positive and this is negative, it's never thermodynamically favored. But when they're the same sign, I don't know. It depends on the temperature. And so let's go ahead and calculate the temperature. Now, if we look at that using that going home to supper equation, and we plug in what we know delta H is given as negative 508.3. The temperature is this little delta G naught. That naught stands for the temperature of 298. Incidentally, this will be given to you in the problem typically. Delta S is given. In this case, they're converted to kilojoules. So we have, instead of the 178 joules per mole Kelvin, it's 0.178 kilojoules per mole Kelvin. And so when we multiply all of this, we get negative 455 kilojoules per mole. And so that's our answer for part A. And the next part asks us, is this process thermodynamically favored? And how would we know? So what do we look at to know if something's thermodynamically favored? We always look at delta G. If delta G is negative, then it is thermodynamically favored, meaning it produces much more products and reactants. And so it is thermodynamically favored, and our justification or our explanation is that delta G is less than 0. Okay, now we have to find QP. Now we're finding Q. If we're finding Q, that means we're not quite sure if we're at equilibrium or not. But find Q if the partial pressures are found to be, and the pressure of PCl3 is 1.14. The oxygen 0.73 atmospheres, and POCl3 is 0.54 atmospheres. And so how do we find Q if we're given all these pressures? And so step 1 is to write our equilibrium expression, or our Q expression. And so in that case, we would write, looking at our reaction, the pressure of P, the products, POCl3 squared, the pressure of the PCl3 squared, and then our oxygen is just the pressure of oxygen. Since the coefficient is 1, the exponent on this one is also 1. And then we plug in all our pressures. So if we have 0.54 squared divided by 1.14 squared and 0.73. And we get a total of 0.31. And so we calculated Q. And our next question is find K. So find K for that reaction at 298. And so if we look at that reaction at 298, what do we have that can help us find the K? So if we look at that, we know Q. We don't quite know if we're at equilibrium. We are finding K to compare the two. And so how would we find K from the information we have? Now, the only thing that will help you is knowing delta G. So if we're finding K, we're going to use our negative Ratlink equation. And so if delta G, let's turn the page again. If delta G equals negative Ratlink, and we plug in all of those values we know after we solve for K. So in other words, this is going to be e to find K. And so this is going to be e to the negative delta G over RT. And if we know this number, we know that delta G, we calculated that in step 1, is negative 455, and I think we found kilojoules per mole Kelvin. We have to get it into joules because the R value is in joules. The temperature is 298, and how do we know that? It's given. And so when we get this number, again, we have a negative and a negative, so we need a positive number right here. We are going to get a K of 5.72 times 10 to the 79. Now, is this what we would expect? Did we expect a really big positive number? When you have a negative delta G, yes, you expect a positive number for K, always a positive number for K, but this number is much greater than 1 because we have a negative delta G. And so, the next question, in which direction will the reaction proceed? Justify your answer. And so, this kind of question is asking us, is it at equilibrium? And how do we know it's at equilibrium? If you look at this, we know Q. We are not quite at equilibrium. This is what the ratio of products to reactants will be at equilibrium, and this is much smaller. This is a much smaller number. And so if Q also equals products over reactants, this number is smaller, which means our reactants are too big or our products are too small. It's going to have to proceed this way until we get a really big product and a really small reactant to the K. And so it's going to proceed from the reactants to the products. This is at the beginning of the reaction. Not a lot of those reactants have reacted yet. And so because, and this justification is really important, because Q is less than K, the reaction will proceed to the right in order to reduce the pressure of the reactants or increase the pressure of the products. You can say either one. And so that is a justification of which way that reaction will proceed. Thank you for learning with me today, and I will see you soon. Bye.